Okay, so today we're going to discuss talking about inverse relations. So here's the definition for an inverse relation. Interchanging the domain and range coordinates of all ordered pairs in a relation give the inverse relation. Similarly, if you have a relation that's defined by an equation with variables, then interchanging the variables will give the equation for the inverse relation. So let's go ahead and do a couple of examples. Here's the first relation that we have. We've got a relation, I'm calling this one G, with just three ordered pairs, -2, 0, -1, 3, and 2, 4. If you think about what we remember about domains, the domain in this case was the x value, so that would be that -2, the -1, and the +2. What we're going to do is interchange that, so that's then going to become the range. So as you'll see, for G inverse, you've just completely switched that. So now -2 is in the range, -1 is in the range, and 2 is in the range. G inverse, so this -1 is not an exponent. It is just a way of representing the symbol inverse. That -1 is just a symbol for inverse. So that's our first example. Let's actually visualize that, something a little bit more interesting. I'm going to graph those points, those same exact points on those examples. The first point was -2, 0. So that's the first one we have is -2, 0. The next point we had was 1, -3. The next point was 2, 4. So that is our relation G. And what I've done here is I've drawn this line y equals x. And what's important to remember about inverse functions is the x and y completely switch. So you're interchanging that x and y. So instead of reflecting it about an x-axis or a y-axis, we're reflecting it about this pink line, the y equals x. So as we have that y equals x, you're just going to almost tilt your head 45 degrees, and then you can see that you can completely reflect that. So there's that first point, the -2, 0, and then 0, -2. Those completely reflected across that line. So the same thing for the other points. We'll do those. So here's the -1, 3, now turned into 3, -1. 2, 4, now turned into 4, 2. And you can see that those in fact did reflect across that line, y equals x. So there's our definition of an inverse relation. So in this case that was our G. This was our G inverse over here. So that's the idea of what an inverse is, but we're going to talk about how to do that with an equation, not just with 3 points, because we definitely have infinitely many points in question. So the next thing that we're going to talk about then is what's called one-to-one. So this is our next definition. A one-to-one relation or function. A function is one-to-one if different inputs have different outputs. And the best way really to visualize that is solely by examples. We'll do the two that we've done the most often in class. Let me draw the first example for you right here. Let's make this a parabola. So here is your y equals x squared. Y equals x squared. In this case right here, let's think about what that means to be one-to-one. When you have something that's one-to-one, it's supposed to be different inputs have different outputs. So I'm going to think about an XY table to talk about my inputs. It's the best way to think about it. You can do this visually as well. Let's start off by just doing an XY table. Some things that we know and love. Plug in the number 2. Tends to be my favorite number. If you plug in 2, what are you going to get? 2 squared is 4. But what happens if I plugged in -2? So this is now a different input. So I have 2 different x values. However, when I plug in -2, I still get 4. So these are different inputs with the same output. So this one is an example of something that is not one-to-one. And that's the abbreviation for one-to-one, just the number 1 instead of writing out the word 1, so 1. Another one that we've used most often in class is the cubed function. So this is the y equals x cubed. Okay, so now I have y equals x cubed. Now let's think about this. We can do an XY table for this as well to try to visualize some of those points. And we all know what it looks like, but let's think about what those look like when we plug them in. If I were to plug in 2, so the number 2, what would I get? 2 cubed is 8. Okay, and then let's do the same thing. Let's try then plugging in -2, plugging in a different x value. What's going to happen? Now, if you plugged in -2, -2 cubed, that gives me 3 negatives. Only 2 of them cancel, so you still have a negative. So the answer there would then, in fact, be -8. So that is in fact a different output. That's negative. There we go. So different inputs will in fact give me different outputs. So this is one example. And you can imagine looking at that picture that all the different x values will in fact give me a different y value. Hopefully that's a little bit more visual from the picture. So this is an example of something that is a one-to-one function. In order to determine if something was a function, we talked about a vertical line test. In order to determine if something is one-to-one, you're going to do the horizontal line test. So if I were to look at this one right here and draw a horizontal line, it did in fact cross twice. So this is something that's not one-to-one. However, you could do the same thing for the y equals x cubed, and that did in fact only cross the graph once. So this is something that is one-to-one. So for a one-to-one, it's the horizontal line test that tells you if it's one-to-one. And then what's nice about one-to-one is that's going to actually give us a new definition. So let's talk about that, something that we haven't used before about these inverses. So let's think about this. If a function is one-to-one, then it has an inverse function. That's going to be the main portion for this chapter right here. If a function is one-to-one, then it has an inverse function. And that's going to be an important part. So if it's not one-to-one, in fact, it does not have an inverse function. So we're going to find f inverse of x when f of x equals negative 2x plus 5. If you remember the definition of inverse, it was interchanging the variables. Okay. So f of x is a fancy way of saying y. As we remember, that was a notation we used. Really, that was a y. So this thing actually was, in fact, a y equals. So when I interchange that, I'm going to turn that y into an x. Equals, and now I have a negative 2, and instead of that x, I'm going to have a y plus 5. And then that's what you're going to solve. So starting from that, you now just have to solve for y in order to find that inverse function. So do whatever it takes to solve for y. I'll give you guys a minute. You should have subtracted 5 from both sides. So x minus 5 equals negative 2y. My negatives aren't coming out very well. And then divide by negative 2, so you would get x minus 5 all divided by negative 2 equals y. Okay, so that's how we did this. We solved now for the y. Once you interchange the x and y, you solve for y. What you have to be really careful with is actually creating this as an inverse function. It's no longer a y equals. In fact, we started with f of x. It's now an f inverse of x. So f inverse of x now equals x minus 5 all over negative 2. Okay, so that is the representation for this. Now this is another thing that you could graph. You could graph each of these and you can realize that they are inverses of each other because they reflect about the line y equals x. So that's the algebraic manipulations for finding that inverse function. Plus 4. There we go. So how do we find the inverse function here? Very similar methods. You're going to be able to look at this f of x. That's a y. You're going to replace that y with an x. You're going to replace these two x's over here with a y. You're interchanging your x and y variables. So now I'll end up with x equals, and then you have y over y plus 4. This is one that's a little bit trickier to solve algebraically, so it's going to just take a little bit more time. So in this example, what we've got to do, excuse me, we've got to eliminate the fractions. Always eliminate the fractions in an equation. So this is technically an x over 1, so I could in fact cross multiply this. I would end up with x times y plus 4 equals y times 1, which is just y. And then I'm going to distribute, same idea as that you've always solved for variables in the past. Get rid of your parentheses, combine like terms. So I have x times y plus x times 4, which is just 4x, equals y. So now I've gotten rid of the fractions. I've also gotten rid of the parentheses. That's always going to be your first step when you're solving any equation. and then you have to get whatever variable you're looking for by itself. In our case, we've already switched the x and y, so now we're trying to get y by itself so we can have an equation for the inverse function. So how do we get y by itself? What the problem is here is I end up actually having y on both sides of the equal sign. So think about those y's and forget about the x's for a second. Think about those x's as just numbers. If those y's were all that you saw as the variables, you would have to get all the y's on one side of the equal sign and all the numbers on the other. So if you think of those x's just as the numbers, it's the same step. Get everything that has a y on one side, everything that doesn't on the other side. So I'm going to take this x times y, and in fact I'm going to try to bring it to the other side of the equal sign so that we can get all y's on one side. So if I do that, I'll end up with 4x equals, and now I have a y minus the x times y. Because again, I took this xy and I brought it to the other side of the equal sign. And then on the other side of the equal sign, you'll notice I've got two different y's, which means there's a y in common. So if I factored out the y, I would be left over with 1 minus x. And I still have a 4x on the other side. And then what you have to do, just like anything else, to get that y by itself, you're going to end up dividing both sides of the equation by whatever's next to that y, in this case the 1 minus x. So I'm going to divide by 1 minus x to both sides of the equal sign. The 1 minus x will cancel here, and I will end up with y equals, and now I have 4x over 1 minus x. So I got y by itself. However, not quite done. You've got to be really careful to always remember that you then also have to write it as function notation. So let's go ahead and do this. All the way down here at the bottom, I'll write that one more time. Technically, instead of y equals, it's actually called f inverse of x. This is the inverse function of f of x, and I now have 4x over 1 minus x. So that is our inverse function that we had. When we write up our original so that we remember that, and we're going to talk about being able to then find the domain. If you remember, our original was f of x, let's see, where do I have that? I had that somewhere earlier. F of x was x over x plus 4. That was the original question. Okay, so what we want to think about is think about things a little bit logically so we can understand what is it that we just did. We certainly switched the x and y. That's one of the main things that we just did. So what else did we do? Really what we did is switch the domain and range. If you remember, x's was the domain, y's were the range, and what we did is we switched them. So we should be able to identify the domain and range of everything. So let's think about the domain and range for each one. So the domain for f of x and the range for f of x, and then the same thing for the domain for f inverse of x, and then the range for f inverse of x. Starting with the domain is always easier. Look at your original question. F of x equals x over x plus 4. You cannot have 0 on the bottom. So that would mean that my domain there was x cannot equal negative 4. Because negative 4 was what gave us 0 on the bottom. And if you look at the domain for f inverse of x, I have 4x over 1 minus x. Certainly in this case you notice that x cannot equal positive 1 because that would give me 0 on the bottom, and again we have to not have 0 on the bottom. And then what we did is we switched the domain and range. So if the domain for f of x is x cannot equal negative 4, then that would mean the range for f inverse is x cannot equal negative 4. So we really are flip-flopping them. And then again, the domain for f inverse was x cannot equal 1, which means the range for f is x cannot equal 1. And you can go through and write those in interval notation as needed as well. So that's another question that you guys will get often, is being able to identify the domain and range of these before you even graph them.